So today, the title of my talk is Quantitative Absorption Measurements and Melt Pool Dynamics, and then this causal link between them. So today, the talk will kind of be in two parts. So the first part, I'll talk about how I make these measurements of absorption and melt pool dynamics. And then the second part will be how these have been applied to simulations and simulation validation. So for the measurement part, this relationship between absorption and geometry has been one that's been looked at for a very long time. And the oldest paper I can find is from 1909. And I like this paper quite a bit because conceptually it's doing very similar things to what I'm doing. So this person wanted to look at the differences in absorption between radiation that fell on a flat plate compared to that fell on a conical cavity. And so that's pictured here in the middle of this diagram. And he even developed a relationship for multiple reflections as a function of the apex angle of this cone. And so that's not that much different to what I'm looking at, except instead of having this perfect cone, I have a vapor cavity that opens up in a melt pool. And this is an X-ray cross-sectional image of an example of one of those keyhole shapes, which I'll talk a lot more later about how we get those. So for some motivation of why this is important, I point out some results from the AM Bench 2018 challenge. So Eddie did a great job of talking about his benchmark challenge and kind of how the AM Bench fits into that as well. And after this challenge was released in 2018, the different participants could write papers about their results. And here's one that I highlight, and I believe this co-author is here, who I don't know personally, so I expect if I misquote or misrepresent this paper, he'll correct me. But the point that they made in this paper, and so here they're comparing these different cases. So these are different single line scans on bare plate and reporting the differences between their predictions and what was actually measured. And they make this point in the paper that an interesting situation from their perspective arose where, because of the data they were given, they had to constrain these calibration parameters, their power fraction and radius ratio, which are related to the beam dimensions that they were given. And so what they claim is all that left for them as a tuning parameter was the absorptivity. And so as an experimentalist, this is great because that means let's fix the absorptivity, right? And focus on that parameter to be one less tuning parameter. So that's what I've been doing for the last several years. And the way that I've been doing this at NIST out here in Boulder, Colorado, is by using an integrating sphere. So that's pictured here on the right. And the way an integrating sphere, essentially works is that it captures all of the scattered light off of a surface, and you can calibrate these detectors so that in an absolute sense exactly how much optical power is coming off of that surface. So here's this cartoon of the integrating sphere. A sample goes at a port on the bottom of the sphere. Directly opposed to that, there's another port, and that's where the high-powered laser comes through and is focused to the surface of the sample. There's two photodiodes, one on the sphere, which captures the off-normal scattered light, another that's up in the, what's actually a commercial weld head that we calibrate as well, so that captures the specularly reflected light. And the way this works in practice, I'll walk through on the left here. And so here's power as a function of time. So we measure the absolute power that comes out of the laser as a function of time. In this case, it's about 120 watts for 10 milliseconds. And then we measure the scattered light. So this is a combination of the calibrated photodiode signals from both of these two photodiodes. Put those together and we get this blue curve here. And then just do a simple calculation where you subtract the scattered power from the power you put in, and the difference there is the power that's absorbed by the material. So here we're in a situation where we're not, there's no light being transmitted through the material, so it's a pretty simple energy balance calculation. You can integrate these quantities, and that gives you, and then take the ratio, and that gives you what's referred to often as a coupling efficiency. So this is a number that you would be, or that's similar to what you would get out of a calorimetry experiment. So we've done this for a while. We've looked at different materials and different situations and been able to pull out some different information. So here's an example of the absorptance as a function of time on a bare solid piece of stainless steel. And some of the general features we see are this spike at the beginning, which is just heating in the solid phase. This dip is a result of melting. And then this really rapid increase in absorption is where this vapor cavity keyhole forms. And so this is the feature that allows multiple reflections to take place. And so we can quantify the effect that has in more or less real time on the amount of light being absorbed. We've also done this in metal powders. So this is for a stainless steel powder for 1 millisecond, not 10 milliseconds, but we see generally the same features. So you see solid phase heating, you see liquid phase dip, and then an increase once you form a keyhole. So what I'll be talking about mainly today is how we've combined these absorption measurements with an integrating sphere with high-speed X-ray imaging. And so this is a technique that many are using. Tao Sun, formerly at APS at Argonne National Labs, was our collaborator here. So at his beamline, they have developed this technique to send an X-ray beam through a material while at the same time hitting it with a process laser. So melting and creating a proxy of the additive manufacturing or welding situation and getting these high-speed images. So what we did is basically ask if we could, bring our integrating sphere and take the simultaneous data of what the vapor cavity looks like, along with recording its absolute effect on energy absorption. So here's an example of what this data looks like. So the top will be the video that you get from the X-ray image. So you see a line here kind of at an angle. So that's the interface between the solid sample below and the atmosphere above, which in this case is an argon, purged argon environment. This tilt is it's a 7-degree tilt that's necessary for the integrating sphere to ensure that the integrating sphere is capturing all the scattered light. And then plotted at the same time below that will be the absorption that we've calibrated simultaneously. So I'll just go ahead and play this. So you see the vapor cavity form in the beginning and then travel along, and the absorption at the same time kind of reaches a steady state when the melt pool does. So I'll pick this apart a little bit later, but this is just an example of the data that we get from these types of experiments. Okay. So we can pick this apart a little bit. So here's an example from a stationary spot, so not traveling, lasers not moving, solid sample. The black data, so this is absorption as a function of time again, is the data that we get from the integrating sphere. And then these orange dots are the absorption at every point in time where we have an individual image from the X-ray imaging. So this is useful. So we can go to these different regimes where we see effects in the absorption and pull out individual frames. So in this early regime where the absorption is about 30%, we can grab one of these frames, which is up here on the top right, and see that you have what we would refer to as a conduction mode situation. And in the same way, we can grab a frame over in this other region where the absorption has more than doubled and see that this nice keyhole is developed in the bottom right. So we can do some image analysis on these keyholes and start to pull out some geometrical parameters, basic things, width, area, depth, and show those at the same time, or overlay those with the absorption data. So what this allows us to do is do some statistical analyses and look for correlations that we haven't been able to do before. So here's an example of this. So this is a correlation coefficient of these different geometrical parameters and how well they correlate with absorption at the same time. And so correlation coefficient of 1 means perfect correlation and 0 means no correlation. And right off the bat, you can see that area of the keyhole is what correlates most strongly with absorption. Depth is not too far behind. So if you had to choose between which to measure and you didn't have access to a synchrotron, measuring depth will get you pretty close to telling you something about absorption. You can also overlay this data with the coupling efficiency. So the coupling efficiency is, this fairly well-known step function behavior with power, where you transition from a conduction mode, fairly low absorption scenario, and then quickly transition to a keyhole scenario where you're absorbing more and more of the incoming light. And you can see how these correlations shift as a function of which regime you're in. So some of these causal behaviors that I kind of alluded to in the title, here's an example of some of those. So here is, again, a single spot exposure on a solid plate. And this is a relatively high power. So you see that very quickly you form this keyhole pretty early on in the 2 millisecond exposure. You move up to this rapid absorption. And so, before we had taken this simultaneous X-ray image data, just looking at the absorption data, we would see these, spikes down in absorption. I call these stalactites. And, we didn't really think they were noise, but couldn't really, definitively say what they were from. So in this particular data set, we happened to capture 3 images at the bottom of 3 of these stalactites. So if you grab an image from, the kind of 90-ish% absorption, we see this really nice, kind of trumpeted shaped keyhole that gives you very high absorption. But if we then go in and take these 3 images where you see this really sudden and rapid drop in absorption, there's a very different picture. So in each one of these cases, we see a keyhole that's, that's collapsed and pinched closed towards the opening. And so this is the causal relationship where this drop in absorption is very clearly from light no longer being able to penetrate as deeply along the keyhole and thus go through as many multiple reflections, and you see a reduction in absorption. And so the other thing worth pointing out here is, it's pretty well known in the literature that when these events happen, when you have these collapses of the keyhole, especially during additive manufacturing where you're rastering at very rapid speeds, you can form pores, and these pores can be frozen in. And so one of the takeaways here is that by looking at light scattering and these really rapid changes, you can see, on the fly, these events that could lead to pore formation. So now we're looking at traveling data, so scan going left to right. So this is the movie that I showed earlier as an example. I don't know if you noticed before, but there was kind of some interesting behavior where at the start of line, we had a relatively deep keyhole, deep and narrow, and correspondingly, the absorption in this regime was relatively high. After some time, the keyhole became more shallow and more open, and fairly stable, and that led to this kind of flattening of the absorption curve at about 50%. The reason that this occurred has been fairly well known in the welding literature. It's kind of a combination of 2 different factors related to these start of line events. So the first is that there's at the beginning of the line, the vapor plume can't essentially go where it wants to go. It's being redirected up by a kind of initially immovable rear keyhole wall. And then at the same time, there's not this large convective flow that is built up that happens at later times that pulls this rear keyhole wall down. And this takes some time, and in our case, a few hundreds of microseconds to develop. We also see this when we add powder. So here's similar scan conditions, just in the presence of powder, and we can see the same, or qualitatively the same behavior, an initial rise in absorption due to a deep, narrow keyhole that then shallows up and leads to a stabilizing of the absorption. So the next question is, how do we use this type of data for simulation validation? And so that's where I'll shift to now and give 2 examples of how we've been working with different simulation experts to try and get this data to where it could be potentially most useful. So the first example is from a low fidelity part scale simulation. Here's the cross section of the data that I showed previously. And so for this, we've been working with a really talented metallurgist at NIST, Nick Daramo, And what he was able to do is cross-section the scan longitudinally. That's the image that's shown here. So you see a melted region at top, an identified heat-affected zone in the middle, and then the wrought section below that. The EBSD image below shows a phase map, and what he found was that there's this beta enriched phase that appears in the heat-affected zone. And the goal, the goal that I'll be talking about today, at least, will be how we tried to understand the origins of this beta phase. And to do that, we reached out to Eddie Schwalbach, who we just heard from, and to see if he could model the situation and calculate the thermal history to determine what was actually causing this beta phase. So Eddie's model that he's developed for a couple of years is this discrete source model. So this is a thermal conduction only model that's capable of giving us the information we wanted, which was namely the thermal history, but also part scale modeling. So it's this trade-off between reducing the amount of physics in order to have a short computation time. So the calibration procedure that he has traditionally used is one where you have a volumetric source shape that you can adjust as kind of a tuning parameter to replicate what is experimentally determined to be the extent of the melt zone. There's also an efficiency factor, which mainly accounts for the fact that the model is not explicitly taken into account radiative losses and vapor losses. So since we had this additional data, namely the absorption data that we were taking at the same time that these parts were made, we also wanted to test a new calibration procedure. So something we're calling the in situ informed procedure. So because we know experimentally what our source shape is, that's something we actually measured before the experiments, let's pin the source shape to match exactly what we know it to be. Also, instead of using this efficiency factor as a tuning parameter, let's replace that with the experimentally determined absorptivity and see how we do. And so the trade-offs here are that the former traditional procedure requires ex situ measurements. You have to cut the material apart, measure the melt pool regime, and then iteratively tune these parameters. And then with this in situ informed procedure, it's potentially real time if you're measuring the light scattering while making these parts. But what's the cost in terms of accuracy? So here is the results for the in situ informed calibration. So the sigma x is the beam dimension in the x direction, and so we pinned that to match exactly the beam profile that we measure. The dashed lines here are the experimentally determined depth of the surface of the melt pool in black, then the interface between the melted region and the heat affected zone in red, and then difference between the wrought and the heat affected zone in blue. The solid lines are the simulation results. So you can see that qualitatively, it reproduces some of these features that we see in experiments. It does a decent job, I would say, of showing where the heat affected zone is. So this red solid line is the interface between predicted between the melt and the heat affected zone. This blue solid line, that's the beta transist temperature. So anything above this blue solid line, you'd expect to see this beta enrichment that we saw in the heat affected zone. So we wanted to quantitatively compare this to this traditional calibration procedure. So that's the results on the right. So here you can see that we've changed, or Eddie has changed this sigma x parameter to be 2.5 times larger than what we know the answer to be from experiment. But it's it's the tuning parameter that's being used. And again, qualitatively, this agrees pretty well with this in situ informed calibration. And so the takeaway here that we kind of determined is that using these tweaking parameters does improve agreement, but we know the changes aren't physical, right? We've had to change the heat source to be something other than what we know it to be. It also requires these postmortem tests and this iterative refinement. Whereas the in situ calibration technique will give qualitatively similar results, but without this ex situ testing and iteration. So quantitatively, the trade-offs here, if you look at the root mean squared error of a combined width and depth parameter, it's a difference of 10.6 microns for the in situ informed calibration and 2.4 microns. So qualitatively similar, quantitatively not as accurate, but if this trade-off is agreeable to you, this is the quantitative trade-off that you'll be making. So the next example that I want to show is looking at a high fidelity multiphysics simulation. And to kind of build up why we were doing this, I'm going to show another piece of data from our X-ray experiments. So this is going to be for a single spot. The laser is going to come in from the top and hit the surface. And then again, at the same time, you'll see the absorption plotted below for a 2 millisecond laser shot. So here you see conduction mode in the beginning, and then the keyhole forms at the time that the absorption takes off, and then laser shuts off and you resolidify. So when I started looking at some of this data, noticed some things in the absorption behavior. And in the beginning of some of these traces at a particular regime of applied laser power, at the initiation of keyhole, you get a fairly single mode oscillation that you can pick out in the data. And at some point after that, it'll transition to a multimodal regime. Another way to look at this is to look at a Fourier transform spectrograph that's shown here on the right for the same data. So this is frequency in kilohertz plotted versus time along the x-axis. And then the colors just represent intensity. And so you see this, fairly obvious multimodal regime in the first part of the keyhole that goes from between about 50 to 30 kilohertz. And then at some point, there's a transition to this much broader multimodal regime over here. And then this is just another way to show this down below. This is the Fourier transform of these two different regimes. So I made this observation. I presented this in kind of a informal way, about a year ago, saying, not really being able to explain this, but saying, this was a thing that we saw. And at this workshop, this happened to catch the eye of Saad Kairala at Livermore, who kind of excitedly got a hold of me saying that, his simulations had been showing similar things, but, until he saw this data, he wasn't actually quite sure that it was real. And so we quickly kind of hashed out this collaboration where I'll send you the exact experimental conditions that I took this data with and see if you can replicate with your simulations this behavior. And then once you've done that, we can start to investigate the origin of these oscillations using the full physics and the much better time resolution that his model afforded us. And once we have this validated model, you can use this to investigate more complicated process parameters. So here's the result of his simulation for the single spot scenario. And so you see this really nice oscillatory behavior, which is close to what we were seeing in our data. And so I'll pause it here to try and do this. To try and walk through what's actually happening. So when the keyhole is fully extended, so the pseudo color here, red is the hottest part. So that's temperature. And then these arrows show the fluid flow that's happening outside of this interface between the keyhole wall and the fluid. So when the keyhole is fully extended, the laser is getting all the way down, you're getting maximum absorption, you're heating most at the bottom of the keyhole. At the same time, you have a cooling of the top of the keyhole. So that starts to show up here in green. And so when that happens in these materials, the surface tension starts to strengthen and leads to the necking of the opening that starts to occlude it. So if you continue this, a little farther, you see that this cooled region at the top is starting to close down. And when that happens, light can no longer get to the bottom of the keyhole, which then starts to cool. Light is again now absorbed near the top where the heating is most strong. And you see this this wave that starts to set up from the fluid flow outside of this hot region, which drives this pressure wave down and kind of continues this cycle of extension, collapse, extension, collapse. So it really is this kind of tug of war between the vapor pressure that wants to push this keyhole open, and surface tension that wants to bring it closed.
Mm.
So we were able to then, or Saad was able to then look at more complicated situations. So here, using this validated model, he's going to do a scan that goes to a turnaround point and reverses direction. And so you see the fairly well behaved keyhole initially. We're starting to turn or slow down to turn around. And at this point, you see that these oscillations start to happen. So this is pretty similar to what we saw in the stationary case. And what's interesting here is you'll see these little pores that develop at the bottom of the keyhole, but because this is a very periodic oscillation, these pores are only temporary and they'll be reabsorbed by the keyhole as it extends. But as it pulls out of the turnaround, these modes shift to instead of single mode, more multi-mode. And that's where you see these pores pinch off and eventually be solidified by the moving solidification front. So the takeaway here is that that we have in this paper is that these multimodal regimes, or what we call the turbulent regimes, these are where porosity occurs. And these periodic oscillations are kind of a harbinger that if the power applied or the energy density that's being applied continues or increases, that you're going to be approaching this turbulent regime. And then by looking at the scattered light, we can see and quantify this periodic regime, or this shift from periodicity to multimodal. So the conclusions, the takeaways from this is that there is this inextricable link between melt pool geometry and absorption, and that you can learn quite a bit by measuring both simultaneously. And in particular, by doing so, that's a powerful package of information that can be used for model validation. And then the last point is that by measuring absorption or just light scattering, you can observe and then hopefully prevent this pore forming behaviors. So the last thing I'll mention is, Eddie had mentioned the AM bench that's coming up in 2022. This is run by Lyle Levine and Gaithersburg. This data, so this combination of absorption and X-ray imaging, is going to be its own kind of standalone challenge for the AM bench, what Lyle's calling a benchlet. And this will be released asynchronous to the regular AM bench data package that I think is coming out in April. This data will be coming out in just after the new year. So if you're interested in working with this, it will be soon available, or separately, feel free to send me an email. So with that, thank you.
Yeah, thanks a lot for these fascinating insights. The talk is open for discussion. We are a little bit behind time, but I think we should allow a few questions. Are there questions in the auditorium here? So can you maybe comment again on the simulations, how they were done? I mean, that was quite impressive. Stefan has a question.
Yeah, no one's more impressed by these simulations than me, especially since I'm an experimentalist. I think it depends on which one you're interested in. Since Eddie's here, if you're interested in in his simulations, I would absolutely defer to him. Details of the high fidelity simulation, I think I would also have to lead to the publications of Saad. I know their group has spent many years fully validating the simulations that they applied here to look at these oscillations.
Yeah, this looks amazing, no?
Oh yeah, I completely agree. I could stare at this all
It almost looks like a hurricane, like this thing.
I mean, the remarkable thing to me, at least, is that this is so representative of what we measured experimentally, right? I mean, our videos were at 50,000 frames per second, and we're looking at oscillations approximately that order in terms of their frequency. And so the fact that he was able to get these oscillations, and then it allows us to kind of interrogate the physics at a much finer time resolution. Yeah, I agree. It's incredible.
Stefan.
Oh, thank you for picking up this thread on the absorption measurement.
Thanks for writing it.
Kind of deprived us of yet another fiddling parameter or fumbling parameter. But I just want to say thank you for picking this up. I think that these type of simulations that you're showing here, Boltzmann is very suitable, and the follow-up talk will be about that. Anyways, thanks for that, and contact me by email whenever you like. We can discuss about the results. Thanks. Bye.
Thank you.